All right. So all the stuff about initial values and antiderivatives has an application, a simple application, pretty quickly. Right? So remember, we talked about if we have a position function, which we call s of t, then we can get velocity. I just completely misspelled that. Velocity, which is v of t. This is just the derivative of s. And we can get acceleration, which we call a of t, which is, v prime of t or s double prime of t, right? Maybe I should write v prime of t here. So what that then means is if I start with acceleration, then I also know that at least, I can get velocity. I can do this by taking the indefinite integral of acceleration, right? I can get position by integrating velocity. Now, the problem with this, you might have already, suspected, is that these expressions here have some kind of, it has an arbitrary constant in it. And if we're trying to model something, we want to model it precisely, right? We don't want arbitrary constants floating around. And so, what we do is, if we have an initial velocity, then there's no arbitrary constant. If we have an initial position, then there's no arbitrary constant here either, right? So let's say, we have an object that's just sort of thrown upward or launched into the air at some point, right? So let's look at the vertical motion here. Okay, so we have the acceleration due to gravity, right? Which, is our famous constant g. Depending on your units here, this is 9.8 meters per second squared, or 32, I believe, feet per second squared. Let me double check that. Yep, 32. Cool. And so if we're just looking purely at the y component of the motion, the vertical component of motion, then, sort of y double prime of t, if you will, or a of t, is going to be, just negative g, right? Okay, well, let's say we give it an initial, I don't know why I put two i's there, initial velocity. Let's say at time 0, v is, we're going to call it v naught, right? Then y prime of t, which is v of t, I get by doing this antiderivative here. Oops, dt. It's one t, please, or 1d. Right, so if I do this, I wind up with minus gt plus c. And we can actually find out that, c has to be v naught. And so the velocity, y prime of t, which is v of t, this has to be, I'm going to write this in this order, v naught minus gt. Okay? Now, if we add on to that the initial position, right? I'm going to call this one y of 0 equals y naught, right? Then, the y of t, this is going to be the integral of our velocity, right? So if I just integrate that as it stands, I'm going to get that, well, I have v naught t minus a half gt squared plus c, right? And I'm going to find out that, well, c has to be y naught, so I'm almost out of room here. Let me zoom in. I can say then that my final model, y of t, is going to be y naught plus v naught of t plus, minus 1/2 g t squared, right? So this is our usual kinematic equation. If you've seen this before, this is our standard, kinematic equation for vertical motion, right? Now, if we were in some other place with some other acceleration, we could just say plus, maybe a naught of t if we're under some constant acceleration there, right? So there's lots of ways to look at this. Let's do a quick example with this. So if we have a baseball thrown upward from a height of 2 meters, so this height of 2 meters here, this means y naught is 2 meters, with an initial velocity of 10 meters per second. Okay, this phrase right here means v naught is 10 meters per second. We want to determine its maximum height. All right, so we know then that y is going to be 2 plus 10t minus, so here we're going to use our g equals 9.8 meters per second squared. So this is going to be minus 4.9 t squared, right? So we want to determine its maximum height. Well, now we're back in the realm of derivatives, right? We want to find the maximum of this function. So one nice thing is we could go for the extreme value theorem kind of thing. We know at time 0 it's at one spot. That's sort of the first place that makes sense. We know we can find the time in the future when this hits the ground, and we'll ignore bouncing because it's never going to reach that maximum height after a bounce anyway. And then we could look for critical values in the middle. We can also sort of reason out here like, all right, wherever this derivative is going to be 0 is where the ball is going to reach its maximum height. So we want to just look for where is the velocity 0, right? So an object can change directions when its velocity is 0. So let's look for y prime. This is going to be 10 minus 9.8t. Set this equal to 0, and we get that t is going to be 10 over 9.8. Right, and that's some number. Let's go ahead and estimate that real quick. So 10 over 9.8. That's about 1.02 seconds. Right? So to determine its maximum height, well, we're just going to plug 1.02 into this function. So this is 2 plus 10 times 1.02 minus 4.9 times 1.02 squared. And this is going to give us an answer in meters. So let's go ahead and compute that. 2 plus 10 times 1.02 minus 4.9 times 1.02 squared. And bam, we get 7.10 meters. So the maximum height is 7.10 meters. All right, well, hope you enjoyed the application here and enjoyed the antiderivatives. And starting in the next class, we will start really getting a feel for what is the sort of cumulative aspect of these integrals?